Bismillahirrahmanirrahim. Assalamu alaikum. Lecture number 3, unit number 2. The title of that unit is Matrices and Determinant. The topic of this video lecture is types of matrices. In this video lecture, we will discuss the types of matrices, different types of matrices. Mainly, there are two types of matrices. One is rectangular matrix and the other is square matrix. So then further, rectangular matrix and square matrix are divided into: rectangular matrix is a column matrix or a column vector is a subtype of a rectangular matrix. Rectangular matrix is a type of a matrices, and these are the subtypes. Row matrix or row vector is also a rectangular matrix. We define these in this video lecture. Square matrix. Now diagonal matrix is also a square matrix. Then scalar matrix and unit matrix are diagonal matrix, and diagonal matrix is a square matrix. So you can say that scalar matrix and unit matrix are also square matrix, because these are the subtypes of diagonal matrix, and diagonal matrix is a square matrix. Zero matrix, which is also known as null matrix, this is also a square matrix. Transpose of a matrix. Transpose is actually an operator. So we always take a transpose of a square matrix. If a matrix is square, so we will take the transpose. So transpose is an operator which is only defined for the square matrices. Upper triangular matrix is also a square matrix. Lower triangular matrix is also a square matrix. Triangular matrix is also a square matrix. Symmetric matrix is a square matrix, and skew symmetric matrix is also a square matrix. So you see that most of the work is on the square matrix. So what is the reason why rectangular matrices are not further studied and square matrices are studied in detail? Inshallah, in coming videos we will define the determinant. So determinants are only defined for square matrices, and most of the work in this chapter is on the concept of the square matrix. So what is the reason that we study in detail the square matrices and not the other matrices? So square matrices are involved in applications, in real world applications. Square matrices are used in technology. If you know, in previous video lectures we discussed that behind every image are actually made from pixels, and these pixels are actually made a matrix. So you see that image, satellite image, or it may be any type of image, it may be a medical image or x-ray, MRI, or it may be any satellite image. So images are actually made from pixels, and pixels are actually make matrices. In computer didn't know the pixels are images, they just know the numbers, and that numbers are actually in the form of matrices. So this is one of the applications, and when you convert image into pixels and then that pixels to become a matrix, so that matrix which you get from the pixels of an image, it may be a satellite image, it may be medical image, MRI, CT scan. So this image, this matrix must be a square matrix. We always get a square matrix. So that's why most of the work is on the square matrix. Most of the concepts are developed on the square matrix. This is the reason. Now if you see it here, so you see that, okay, now this is a little, okay, now you see that this is I am sharing the left top screen. It is not in straight position, but you can see it from here. This is an image, a complicated image. This image contains so many homes, there are some persons, trees. So if you convert this image into pixel, image are compressed of pixels represented by number. So you see that when you convert that image into pixels by computer, the program, the software which used to convert an image into pixels are called MATLAB. Mat is taken from matrix and lab is laboratory. So matrix laboratory is a software which convert the images into their pixels in computer. So you see that the pixels are actually the square blocks. You see that these square blocks, and these each square block is actually a pixel. When you zoom this or when you convert through the that software this image, so actually for every pixel we have a number. So when you convert that pixels into numbers, so you see that for the first pixel, you see this is square brackets, this wide square bracket, this is 64 and so on. So you see these pixels are converted into this matrix. Now if you see to this matrix, this is a square matrix. A square matrix is those matrices in which the number of rows and the number of columns are equal. So here if you see, there are 8 rows and there are 8 columns. So you see the image is converted into a matrix which is a square matrix. So that's why in application we use square matrix, or in other words you can say that the matrices that we get from a different satellite or medical images are actually square matrices. So that's why we need the study of the square matrices for the advancement of technology. We didn't need rectangular matrix or the types of rectangular matrix. So that's why most of the work is on the study of the square matrix. This is the reason behind that we are studying square matrices are in detail. Now moving toward the topic, now I am defining these matrices one by one. What is the rectangular matrix? A matrix in which the number of rows and number of columns are not equal. So that matrix is called rectangular matrix. Now rectangular matrices, before to discuss the rectangular matrix, we know that if I take a journal matrix, a journal matrix of order, a journal matrix of order m by n, so that may be written as, let's say, denoted by capital A. We know the matrices are denoted by capital letters. So this is A11, A12, A13 and so on up to A1n, A21, A22, A23 and so on up to A2n, and this is so on up to AM1, this is so on up to AM2, this is so on up to AMN and so on up to this is 3 and AMN. So this is a matrix of order m by n. This matrix contain m rows and n columns. I already explained that why I am writing every element of this matrix in the form of a, and there must be some subscript which contain two numbers. So the first number in the subscript for the row and the second one for the column. If you choose any number with the subscript, so that subscripts are telling you that the number lies in that row and that column. So this is the reason that we are always taking the journal matrices in this form. So we in previous lecture discussed that we always consider throughout this chapter, matrices of general form like this: Aij, and this is of the order m cross n. This is not, this is read as m by n. So this is the compact form of writing this matrix. You can also write I runs from 1 up to m and j runs from 1 up to n, but this is the compact form of writing this matrix. So we will use this form while defining the different types of matrices. Okay, now column rectangular matrix, a matrix in which the number of rows and number of columns are not equal. So such matrices are called rectangular matrix. Rectangular matrix, number of rows not equal to number of columns. It means that if you have a journal matrix of order m by n, so this matrix is said to be a rectangular matrix if m is not equal to n. Mean m is here the number of rows and n is the number of column. So if a matrix has different rows, number of different rows and number of different columns, so that matrix is called rectangular matrix. So this is the definition of a rectangular matrix. So for example, let's say matrix A, these are the examples of the rectangular matrices. A is equal to 1, minus 2, 3, 4, 5, minus 6. So you see that the order of this matrix is 2 by 3. There are 2 rows and 3 columns. So you see that this is the value of m and this is the value of n. So m is not equal to n because 2 is not equal to 3. So that's why this matrix is called a rectangular matrix. Okay, so this is the definition of a rectangular matrix. Now the types of rectangular matrices. The types of rectangular matrices: column matrix, which is also known as column vector. So the definition of the column matrix is a matrix which contain a single column. Mean the arrangement of the elements in that matrix are in a single column. So a matrix in which there is only one column. For example, 0, let's say this is a matrix A. You can name it with B, C, D, it's your choice. So this is, let's say, square root 3, minus 1, 1 by 2. So the order of this matrix, there are 4 rows and 1 column. So you see that the number of the columns are 1. So that's why this matrix is called a column matrix or a column vector. Column matrices are also called column vector. In general, how you can write a column matrix. So in general, we write it like this: m cross 1. So you see that this is the this 1 represent the number of columns. So this is a matrix in which there are m rows and just 1 column, or you can write in general form, you can write a 1 1, a 2 1, a 3 1, and so on up to a m1. So this is a matrix of order m by 1. I already explained that the subscripts are 2 numbers with each element, and the first number of the subscript is for the number of rows and the second one is for the number of the columns. So throughout the elements of this matrix, you see that the second number is 1 1 1 1. So that shows that this matrix contain a single column. So that's why this matrix is called a column matrix or column vector. Now the second type of a rectangular matrix is row matrix. Row matrix. Row matrix. This is a type of a square matrix. Now a matrix containing only one row, so that matrix is called row matrix. For example, if I give you example, so the example of that row matrix, let's say B is a matrix and the arrangement of the elements of that matrix are in a single row. You see that there is only one row and four columns. So that's why this matrix is a row matrix, because it contains a single row. In general, how you can represent in general row matrix Aij, the order of this will be 1 cross n, mean there are n columns and just one row, or in other words you can write this B is equal to A11, A12, A13 and so on up to A1n. So you see that the first number in the subscript is for the representation of the number of rows. So you see that all the elements of this matrix having first subscript is 1, here is 1, here is 1, here is 1. So it indicates that this matrix is only contain a single row. So that's why this matrix is called a row matrix, or this matrix is also named as row vector. So these are the types of rectangular matrices. Now after that we will discuss the square matrices. So the definition of a square matrix is a matrix in which the number of rows are equal to the number of columns. Now the square matrices, what is the definition of a square matrix? Definition of a square matrix: when the number of rows, this is the simple definition, the number of rows is equal to the number of columns. So then that matrix is called a square matrix. For example, if I consider a square matrix of order m by n, so that matrix is said to be square if the number of column is equal to the number of rows. For example, in general a matrix of order m by n is called square matrix, if m is equal to n. If this is m by n is the order, so what does it mean? It means that there are m rows and n columns. So the definition of the square matrix is the number of rows is equal to the number of columns. So if this number of rows is equal to the number of columns, then that matrix are said to be square matrix. So in general we write a square matrix, let's say A, so this is A11, A12 and so on up to A1n, and this is A21, A22 and so on up to A2n, and this is AN1, AN2 and so on up to ANN. So you see that there are n rows and n columns. So the order of this matrix is n by n, or we can simply say that the order of this matrix is n. Order of A is n. Instead of n by n, in case of the square matrices, we will just say n is the order of this matrix. So from that we get that this is a square matrix. Now the example of a square matrix, let's say a particular example of a square matrix. A is equal to 1 minus 3 1 2 4 minus 1 3 5 6. This is a square matrix because it contains 3 rows and 3 columns. The horizontal arrangements of the elements are called rows and the vertical arrangements of the elements are called columns. So there are 3 rows and 3 columns. So that's why this matrix is called a square matrix. In square matrices, if you see to the diagonal of the square matrix, this is the diagonal of the square matrix. You see where the elements for which I is equal to j mean, you see that this a11 lies in first column and first row. So I equal to j, I for the number of row and j for the number of the column. So 1 1, this lies in the first row and first column. A22, this lies in the second row and second column. There must be a33 lies in the third row and third column, and so on. ANN mean this lies in the nth row and nth column. So this is called, these elements lies on the diagonal, and this diagonal is called principal diagonal or main diagonal or leading diagonal. This diagonal is called principal, main or leading diagonal, and the elements which lies on this diagonal are said to be the elements of principal diagonal. Throughout the chapter, instead of name this diagonal main or leading diagonal, we will name it a principal diagonal. So a11, a22, a33 up to ann are the elements of principal diagonal. So we can write aij are the elements of principal diagonal fi equal to j. You see that on this diagonal I equal to j, 1 1 2 2 and nn and so on up to nn. So the aij mean the elements of this matrix are said to be the elements of the principal diagonals fi equal to j. So here this element is on the place of a11, this on the place of a22, and this is on the place of a33, because this lies in the first row and first column, this lies in the second row and second column, this lies in the third row and third column. So the the principal diagonal elements in matrix A are 1, 4 and 6. These are the principal diagonal elements. Okay, so if I equal to j, so those elements of matrix of a square matrix, remember we are discussing principal diagonal for the square matrix, so that is called the elements of the principal diagonal if I equal to j, mean the number of row and the number of column are equal. So this is the square matrix. Now after a square matrix there is a diagonal matrix. You see that diagonal matrix. Now we will discuss. So diagonal matrix is a subtype of a square matrix. A square matrix is said to be a diagonal matrix F. On the diagonal we have non-zero and the rest of the element other than the principal diagonals are zero. So diagonal matrix is actually a square matrix. This is a square matrix, but such type of a square matrix in which the principal diagonal elements are non-zero, at least one of them is non-zero and the rest of the elements are zero. For example, if I take -1 0 0 2, so you see that This is a square matrix of order 2. Instead of saying order 2 by 2, we just say order 2 because this is a square matrix. So this is the principal diagonal of this square matrix. Now this is the principal diagonal of this square matrix. So you clearly see that on the principal diagonal the elements are non-zero. Here a1 1 is equal to -1 and a2 2 is equal to 2, and the rest of the elements, this element is a1 2, this lies in the first row and second column, so this is will be denoted by a1 2, and this is a2 1 because this lies in the second row and the first column. So the rest of the elements are 0. So a matrix in which a square matrix, it is a type of a square matrix, remember, is said to be a diagonal matrix if the principal diagonal elements are non-zero. So what does it mean? It doesn't mean that all of the principal diagonal elements must be non-zero. It means that at least one of the principal diagonal element must be non-zero, and if the rest of the elements, mean non-diagonal elements, are 0, then such type of matrix are said to be diagonal matrix. For example, in general, if I say B is equal to Bij is a matrix of order, let's say M, this is a matrix of order M, so it become a square matrix because the number of rows and the number of columns are equal. So this matrix is said to be a diagonal matrix if Bij is not equal to 0 for all I equal to j. This is the definition. What does it mean? It means that the elements of this matrix are non-zero for all I equal to j, and Bij equal to 0 for all I not equal to j, mean the rest of the principal diagonal elements, all the elements are 0. Here for all you will write for some because we say that at least one of the principal diagonal, so this must be for some. So if I say example, let's say B, so you see that this must be B1 1, B1 2 and so on up to B1 M, and this is B2 1, B2 2 and so on up to B2 M, and this is BM1, BM2 and so on up to BMM. So what does it mean? If these elements are at least one of them, I write for some I equal to j. So on the principal diagonal you see that I is equal to j. So here if one of them is non-zero and the rest of all elements are 0 for I is not equal to j, and other than principal diagonals the subscripts is not equals in the elements in the subscripts are not equal. You clearly see that this is 1 2 1 m. So this is the definition of a diagonal matrix. Now I consider a unique example. Let's say C is equal to 4. So this is a matrix of order 1 by 1, or you can say 1. So this matrix is a square matrix because here there is only one row and one column. Now this square matrix is also a diagonal matrix because on the principal diagonal, this is the principal diagonal. So on the principal diagonal the element, there is only one element which is non-zero, and the rest of the element there is nothing. So that's why this is also a diagonal matrix. This is also a square matrix, but in square matrix this is also a diagonal matrix. So this is the definition of a diagonal matrix. Now after the diagonal matrix, scalar matrix, which is the subtype of the diagonal matrix. So scalar matrix, for example, I am discussing scalar matrix now. Scalar matrix, let's say B is equal to Bij of order M, is a square matrix, because if a scalar matrix is a diagonal matrix, so it must be a square matrix. So you see that when I write order m, so it automatically mean it is a square matrix. So this must be a diagonal matrix. This must be a diagonal matrix. So what does it mean? This matrix is a square matrix in which the elements of the principal diagonals are non-zero and the rest of the elements are zero. So how you can write that? We write this. This is the definition of the principal. This is the definition of the diagonal matrix. Bij is equal to there must be this is non-zero for some I equal to j, and 0 for all I not equal to j. So this is the definition of the diagonal matrix. Now the diagonal matrix is said to be a scalar matrix if all these non-zero elements are equal. If all these non-zero elements are equal. For example, let's say b is equal to, let's say 3 0 0 0 3 0 0 0 3. So you see that this is a square matrix of order 3. This is a diagonal matrix because on the principal diagonal the elements are non-zero and the rest of 0. But you see that the elements on the principal diagonal are non-zero and all are these elements are equal. So if these non-zero elements are equal to some constant k, you see 3 3 3 10 10 10 20 20 20, so this type of a diagonal matrix is said to be a scalar matrix. This type of a diagonal matrix is said to be a scalar matrix. For example, in journal, how you can write it? In journal, let's say I write b, so that will be equal to k 0 0 and so on up to 0 0 k 0, so on up to 0 0 0 k, so on up to 0, so 0, this is 0 0 and so on up to k. So you see that this is actually a diagonal matrix of, let's say, order m by n, mean order m. This is a diagonal matrix because on the diagonal we have non-zero and rest of the diagonal we have 0, but on the diagonal the non-zero are equal, the non-zero elements are equal. So such type of diagonal matrix are said to be scalar matrix. Such type of diagonal matrix are said to be a scalar matrix. Now if this scalar is equal to 1, now if this k, the value of k is, let's say, 1, so that type of matrices are said to be unit matrix or identity matrix. Unit matrix or identity matrix. So let's say A is a matrix ij of order, let's say, n. So the definition of the unit matrix must be, this matrix is said to be unit matrix if aij equal to 1 for all I equal to j, mean on the principal diagonal all the elements are non-zero and all of them are equal to 1 and the rest of the elements are 0 for all I not equal to j. This is notation for all. This is the notation for all. So these elements are such type of matrices are called unit matrix or identity matrix. Remember, unit matrix are denoted usually by capital I. If the order of that matrix is n, so here you write small n. So this is the notation for this matrix. I denote it with a capital letter A, but there is a special notation for the unit matrix or the identity matrix, which is capital I, and you may write n, or if the order is specified from the context, then you just write I instead of in. If the order is specified, if the order is known in the context. So the journal identity matrix may be denoted by in or I. If you know the number of the if you know the order, then you just may write I. So this must be 1 0 0, so on up to 0 0 1 0, 0 0 0 1 0, and so on up to 0 0 0, and so on up to 1. So you see that this is actually a diagonal matrix as well as a scalar matrix. But in scalar and diagonal matrix, the elements are on the principal diagonal is same and equal to 1. So such type of matrix is a scalar, is said to be identity matrix. So I1, this is also an identity matrix of order 1. Identity matrix of order 2 will be 1 0 0 1. Identity matrix of order 3 1 0 0 0 1 0 0 0 1. So from here we write an important note that every identity or unit matrix is a scalar matrix. This is one point, and every scalar matrix is a diagonal matrix. So this implies that from 1 and 2 we can say that every identity matrix is a diagonal matrix as well. But for the diagonal matrix, there is only one condition, that a square matrix in which the principal diagonal elements are non-zero for some I equal to j, and the rest of them are 0. So they are called the diagonal matrix. And scalar matrix is also a square matrix, but it is such type of square matrix that it must be a diagonal, but on the principal diagonal the non-zero elements are must be equal, and all of the diagonal elements in case of the scalar matrix must be non-zero and they must be equal. And for the identity matrix, which is a scalar matrix as well as a diagonal matrix as well as it is a square matrix, so the diagonal elements are non-zero and all of them are equal to 1 and the rest of them are 0. So this is the discussion about the diagonal matrix, identity matrix, which is also known as unit matrix, and a diagonal matrix. Now moving towards the zero matrix, a matrix in which all the entries or all the elements are 0. So that matrix is called zero matrix or null matrix. Now zero matrix, which is also known as null matrix, a matrix in which it must be a square matrix. It is also a square matrix. So you see, it may be other. You can write a rectangular matrix that must also be a zero matrix. But you know, we are studying the square matrices. So whenever if you are dealing with a square matrix and you need a zero matrix, so you must attach a square zero matrix or a square null matrix with that. So if I write 0 0, so this is a row vector, but this is also a zero matrix because all the entries of this matrix is 0. If I write the order of this is 1 by 2, if I write 0 0 0 0, so the order of this is 2. So this is also a null or 0 matrix because all of the elements of them are 0. Remember, the 0 matrix or null matrix is denoted by capital O, and you may write the order here, but if the order is clear from the context, then you just denote the 0 matrix by just capital O. So this is the notation for the 0 matrices. Now next, transpose of a matrix. How we can take the transpose of a matrix? Transpose of a matrix. Let's say A is a matrix, a square matrix. For example, I am considering it may be a square matrix or it may be not, but we are always dealing with a square matrix, so that's why we discussed a transpose for a square matrix. But you can also find out the transpose for the rectangular matrix. For example, if I consider a rectangular matrix of order let's say 3 by 2 in general, so you see that this is a matrix of order 3 by 2. There are 3 rows and 2 columns. So how you can find out the transpose? You need to convert the rows into columns and column into rows. The choice is yours. You want to convert the rows into column or column into rows. But by converting rows into column or columns into rows, that matrix will become the transpose of the given matrix. So how you can find out the transpose? Convert the rows into columns. So let's say the first row, so first row is now written in the first column. You see that this is the first row, now it is written in the first column. Now the second row will be written into second column. The third row will be written in the third column. So you see that when you take the transpose of a matrix, the order of the transpose of the matrix will be 2 by 3. It is clear from the definition that you are changing rows into columns or columns into rows. So when you change row into column or column into row, so this order will be reversed. The order is here 3 by 2, so here the order will become 2 by 3. So this is the definition of a transpose of a matrix. So in general, if Aij is maybe a square matrix and it may be not a square matrix. Let's say this is a matrix of order m by n. It may be square, it may be not square. So the transpose of this matrix is, let's say, this is denoted by a power t. You can write small t in the power of a. So this is notation for the transpose, and it must be some other matrix, so you can name that with b or something else also. So let's say this is equal to bij, this will be equal to bij of order m by n, because you are changing the rows into columns and columns into rows, so the order must be changed. If the order of the given matrix is n by m, so the order of its transpose will be m by n, because the order is changed. Here there are n rows and m columns, so here must be m rows and n columns. So here bij will be equal to ji. So you see that the row is changed into column and column is changed into row. I already explained that the first subscript is for the row and the second is for the column. So in case of the transpose, I will be changed into j and j will be changed into I, because in the definition of the transpose you are changing row into column and column into row. So this is the definition of a transpose of a matrix. Triangular matrix, upper triangular matrix and lower triangular matrix and triangular matrix. Now when I consider a square matrix, let's say now I am discussing a upper triangular matrix. The definition of upper triangular matrix, lower triangular matrix and triangular matrix are related to each other. So I am considering a square matrix. Let's say this is 2 3 1 0. This is example for the upper triangular matrix. I will define the definition. I will define that after discussing this example. So you see that this is a square matrix of order 3. In this square matrix, this is your principal diagonal. You see, this is your principal diagonal. Now, below the principal diagonal, you clearly see that all the elements are 0. This is the principal diagonal. This is the principal diagonal, and below the principal diagonal you see that all the elements in this square matrix are 0. So such type of matrices in which all the elements below the principal diagonal are 0, below the principal diagonal, below the principal diagonal are 0, all the elements below the principal diagonals are 0, then such type of matrices are called upper triangular matrix. Upper triangular matrix. Now if I write this 3 by 3 matrix in a journal form, A11, A12, A13, A21, A22, A23, A31, A32, A33. These subscript actually represent the position of the matrix, the position of the element in the matrix. So this is your principal diagonal. So this is your principal diagonal, PD for principal diagonal. Now below the principal diagonal we have A21, A31 and A32. So if this is equal to 0, this is equal to 0 and this is equal to 0, so then such type of matrix is called a upper triangular matrix. So the definition becomes, in this case you see that I is greater than j, 2 is greater than 1, I is greater than j because 3 is greater than 1, I is greater than j because 3 is greater than 2. So A is equal to Aij, this is the general definition of order n or n, it must be a square matrix, is said to be upper triangular matrix if Aij is not if Aij is equal to 0 for all I greater than j, because below the principal diagonal you clearly see that I is greater than j, I is greater than j. So this is the general definition of the upper triangular matrix. If Aij is equal to 0 for all I greater than j. So the alternate meaning of this is the mathematical form. So you must convert every definition into some mathematical structure. This is the beauty of the mathematics. So this is the definition of the upper triangular matrix. This definition says that below the diagonal elements must be 0. This is the mathematical way of writing that below the diagonal elements are 0. So that matrices are called upper triangular matrix. If now I am discussing the lower triangular matrix, so if I consider lower triangular matrix, the next definition is for the lower triangular matrix. Now if I consider an example 2 0 0 minus 4 5 0 2 3 1. So in this matrix you see that this is a square matrix of order 3. This is the principal diagonal, and above the principal diagonal you see that all the elements are 0. So such type of, this is the principal diagonal, and in this case above the principal diagonals all the elements are 0. So such type of matrices in which the all the elements above the principal diagonal are 0, so such matrices are called lower triangular matrices. Now if you convert this into the journal form, so this is A11, A12, A13, A21, A22, A23, A31, A32, A33. So you clearly see this is your principal diagonal, and above the principal diagonal we have A1 2, A1 3, A2 3. So here you see that I is greater than, sorry, I is less than j, 1 is less than 2. Here also I is less than j, and here is also I is less than j. So you say you can now know that above the principal diagonal the I is greater than j, mean above the principal, if an element lies above the principal diagonal, so it must be a row of that element must be less than the column. So I is less than j, you see that 1 is less than 2, 1 is less than 3, I is less than j, 2 is less than 3, I is less than j. So the general definition, a matrix Aij of order n is said to be lower triangular matrix if Aij equal to 0 for all I is less than j. If I is greater than j and Aij equal to 0, so that matrices are called upper triangular matrices. And if Aij equal to 0 for all I less than j, so that matrices are called lower triangular matrices. And the triangular matrices, if a matrix is a lower triangular matrix or if it is a upper triangular matrix, so that is called triangular matrix. So this matrix is also a triangular matrix because it is a lower triangular matrix, and this matrix is also a triangular matrix because it is a upper triangular matrix. So upper triangular matrices and lower triangular matrices are called triangular matrices. Here you must note an important point that diagonal matrices are triangular matrices. Mean diagonal matrices is a, here this is an important note for eta, that diagonal matrix is upper as well as lower triangular matrix, or you can say diagonal matrix is a triangular matrix. So this is an important point. Every diagonal matrix must be a rectangular matrix because it is also upper triangular matrix as well as lower triangular matrix. So you can simply say this is a diagonal matrix. Diagonal matrix is a square triangular matrix. Now the last two definitions, symmetric matrix and skew symmetric matrix. So symmetric matrix, so let's say A is a matrix Aij of order n. So if A transpose is equal to A, so then that matrix is said to be symmetric matrix. This is the simple definition. If you take the transpose of a matrix and that transpose is equal to the given matrix, so that matrix is called symmetric matrix. Now what is the example? The example of the symmetric matrix is A is a given matrix which is 2 3 6 3 1 minus 5, this is 6 minus 5 4. So this is a square matrix of order 3. Now you need to check this is a symmetric matrix or not. So for the symmetry of the matrix you need to take the transpose of the given matrix and then you check this relation that if the transpose is equal to the original matrix, the matrix is said to be symmetric matrix. So now how you can take the transpose of a matrix? Transpose of a matrix are actually you need to interchange the rows or you need to interchange the column into rows or rows into column. The choice is yours. So I am changing rows into column. So this first row is converted into the first column. You see the second row I am writing in the second column. The third row I am writing in the third column. So when the number of rows is interchanged into the number of columns, so that matrix become the transpose of a matrix, and this is the notation for the transpose of a matrix. You clearly see that the transpose is equal to A, and the order of them is also 3 by 3. So you clearly from here you clearly see that A transpose is equal to A. So therefore this matrix, the given matrix A, is a symmetric matrix. Now skew symmetric matrix, the last definition: a matrix A ij, let's say of order n, is said to be symmetric, skew symmetric matrix. Skew symmetric matrix if A transpose is equal to negative times of A. So this is called the symmetric matrix. For example, I am considering an example: A equal to, this is an example, A equal to 0, 2, 3, minus 2, 0, minus 4, minus 3, 4, 0. Now take the transpose of this. So the first row will be converted into first column, the second row is converted into second column, and the third row is converted into the third column. Now take minus common from this matrix. So by taking minus common from this matrix means you need to take minus common from each element. So you write minus here. So this is plus 0, so it become minus 0. Minus 0 means 0. This is minus 2, so that become plus 2. When you are taking minus from, or taking any scalar constant from the matrix, taking common any scalar constants from the matrix, you need to take common that from all the elements. So if I taking minus common from the matrix, so it means that you need to take that minus common from every element. I am taking minus common because to check this definition. So this is become plus 3, this will become minus 2, this will be 0. If I write minus 0, so that is 0. This become minus 4, this will become minus 3, this will become plus 4, and this will become 0. So you see that this is A transpose, this minus, and if you see here, this is equal to A. So you see that A transpose is equal to minus times A. So that's why this matrix is said to be skew symmetric matrix. Now if you see to the diagonal of a skew symmetric matrix, the diagonal of a skew, principal diagonal of a skew symmetric matrix contain all the elements equal to 0. This is a property of the skew symmetric matrix. How you can verify this property? You see that if I consider a square matrix, so A1 1, A1 2, and so on up to A1n, A2 1, this is A2 2 up to A2n, this is AN1, AN2, and so on up to ANN. So here the diagonal elements are A1 1, A2 2, A3 3, and so on up to ANN. Or you can just write AII, because I equal to j, so you may write AII for all I equal to 1, 2, 3 up to n. Now when you take the finding the skew symmetric matrix, or when you are checking that the matrix is skew symmetric or not, so you see the skew symmetric matrix, in case of the skew symmetric matrix, in case of a skew symmetric matrix, Aij will be equal to minus Aij, Aii will be equal to minus Ii. Remember this point, because by the definition you clearly see that A transpose is equal to minus times A. So if there is a 1 1, so in the transpose you may do the definition A equal to minus time A transpose. This is also the definition of a skew symmetric matrix. So let's say in the first row and the third column, first row and third column, there is A1 1. So here there will be in first row and third column you will get this minus times A13, minus times A13. If here is A21, so necessary there will be A minus A 2 1. If there is a 2 2, so there must be minus a 2 2. So you see that aii will be equal to minus aii. So this implies that now this implies that okay, this must be no, this is not true for all. This must just true for the diagonal elements. This just true for the diagonal elements. So now if you shift this on the right side, so this will become aii, which is equal to 0. So this implies that 2aii equal to 0 implies that aii equal to 0. So it means that in case of the symmetric matrix, all the diagonal skew symmetric matrix, all the diagonal elements are 0. So you see it from the example also. Now these are the three important points for the eta. In skew symmetric matrix, all the diagonal elements are 0. Remember this point. This is a skew symmetric matrix. All the diagonal points are 0. I discussed this point before. The diagonal matrices are both upper and lower triangular matrices, mean triangular matrices. And this is an important point. This absolute is for the determinant of a matrix A. So if a matrix is a diagonal matrix, so how you can find out the determinant? Now let's say A is a diagonal matrix. Let's say A is a diagonal matrix 1 0 0 0 0 4 0 0 0 0 7 0 0 0 0, and let's say this is a 1. So you see that this is a diagonal matrix. Clearly you see this is a diagonal matrix. This is a diagonal matrix. So diagonal matrix, this is an important point for eta. Now you know the determinant is denoted by this bars. So this bars of A denotes the determinant. Now how you can find out the determinant of this matrix? The order of this matrix is 4 by 4. So you know the determinant of 2 by 2 matrix when you multiply the diagonal elements and minus times the non-diagonal. So that become the definition for the determinant of a square matrix of order 2. But when the order of a square matrix is more than 2, mean square matrix of order 3, square matrix of order 4, square matrix of order 5, square matrix of order 6, and so on. So how you can find out the determinant of those matrices? So for that we discussed in detail, inshallah, in coming videos the concept of cofactors and minors. But before to discuss that, if a matrix is a diagonal matrix, so you need just to multiply the diagonal numbers, the diagonal elements, and you will get the determinant. It must be verified from the definition of the cofactor and minors, but this is a very important property, and it is a very important for the eta, because if you want to find out the determinant of 4 by 4 matrix, so it is so lengthy process when you are applying the method of cofactor and minors. But if it is a diagonal matrix, so you need just to multiply the numbers of the diagonals, the elements of the diagonals, and you will get the determinant. So 1 multiplied by 4 4, 4 multiplied by 7 28, 28 multiplied by 1 you will get 28. So 28 is the determinant, and this determinant is not equal to 0. So that's why this is a non-singular matrix, and you can find out the inverse of this. We will discuss this point in the upcoming videos. So if a matrix is a determinant matrix, if a matrix is a diagonal matrix, so for the determinant of that diagonal matrix you need to multiply the diagonal elements. When you multiply the diagonal elements you will get the determinant. So in general, if A is a diagonal matrix, then A determinant is equal to product of diagonal elements. So this is the extra point which I explained. So these are the types of the matrices. Thank you.